This screencast continues our discussion on intermolecular forces. It also talks about isomers, what they are, and how their intermolecular forces are different. So we'll start off talking about viscosity. So viscosity is a resistance to flow. You can think of syrup, like you would put on pancakes, would be a very viscous liquid. It has very high resistance to flow compared to water. If you heat up syrup, though, it ends up becoming less viscous. So viscosity all has to deal with the intermolecular forces. The stronger the intermolecular forces, the greater the resistance to flow. Also, the longer molecules are, the longer chains they form, the more tangled they can get in one another. They also have larger electron clouds that are more polarizable, and that will increase their viscosity. If you look at the example here, we have glycerol, and it has 3 OH groups. Each of those has the ability to hydrogen bond, so really strong attractive forces here, which is going to make glycerol a viscous liquid. Now, let's talk a little bit about isomers. The prefix iso means equal. Think about an isosceles triangle. They have 2 equal sides. So an isomer is a substance or substances that have the same or equal chemical formulas. There are 2 types: structural isomers and stereoisomers. We'll talk about structural isomers first. So structural isomers have the same chemical formula but different arrangement of the molecules. So I have C3H6O. And there are a couple of different ways that you could draw this structure. One might look something like this, where you put the double bond to the oxygen off of the middle carbon. This is an this is a ketone and has its own sort of properties. I could also choose to put that double bond in another spot. So I could put it on this last carbon right here. Still the same structural formula, but the double bond to the oxygens on a different carbon. This makes this molecule right here an aldehyde. Ketones and aldehydes are pretty similar on a lot of different points, but aldehydes are much easier to oxidize than ketones are. Ketones tend to be oxidation resistant. So, and that's just by moving the double bond to the oxygen. So let's look at another example. Here I have 4 carbons and 10 hydrogens for C4H10. And this would be, if it's got 4 carbons, it's going to be bute, and it all has single bonds, so it's butane. And this is the structure for butane, where we have all 4 of those carbons bonded and they're filled up with their hydrogens. I'd like for you to take a moment and see if you can draw a structural isomer of butane. So you can pause the screencast, give it a shot. Hopefully you came up with something that looks a little bit like this. This one is isobutane, and it has its own little properties. Butane over here has a boiling point of like -1 degrees C, and isobutane has a boiling point of -12 degrees C. So just in the way that these elements are put together or arranged does give them different intermolecular forces. Because this chain here is shorter, it is less polarizable than this long butane chain. So it's going to have slightly lower London dispersion forces, and that's all that we have that's going on here, since we have just carbon-hydrogen bonds and they're all pretty symmetrical. Okay, let's look at stereoisomers. These have the same chemical formula and the same arrangement of the atoms, but they differ in spatial orientation. So if I look at, so these would be dichloromethane. If we look at these, or actually ethane, then what we're going to have, we've got carbon double bonded to carbon, and then we have 2 chlorines off of each of those and a hydrogen off of each of those. So in this particular arrangement, the carbon-hydrogen bond isn't too terribly polar, only slightly polar. And when we look at different types of molecules, we generally ignore the hydrogens, and we look at the things that are other than hydrogen that are bonded to them. In this case, the chlorines have this arrangement. Over here at this model right here, we have the chlorines here on the same side of the molecule. Both of them seem symmetrical, but really only one is when we look at the way the electrons are being pulled. So we generally will look at a shape kind of like this, and we end up calling and then the other side ends up looking like this. Again, we're only highlighting the bonds that are to something other than hydrogen. The one over here on the left is called a trans. So this would be trans dichloroethene. And it lets us know that the chlorines are on opposite sides of the molecule. Because the electrons, and these are being polar bonds, that chlorine's pulling on those electrons, they're being pulled in different directions. So you can see here that chlorine's pulling on the electrons away from each carbon. They're being pulled with equal force because they're both chlorine, but they're being pulled in opposite directions. So the trans version of this molecule is going to end up being nonpolar because the dipoles cancel out. The cis version, and that's what we call it when the interesting atoms, or the atoms that are not hydrogen, are on the same side of the molecule. If you see the way the electrons are being pulled, they're both being pulled in the same direction, away from those carbons in the same direction, so they don't cancel out. So cis dichloroethene is going to end up being polar. This would translate into a difference between boiling and freezing points, vapor pressure, and all of that, because the trans version is going to only have London dispersion forces, and the cis version is going to end up being polar, so it would end up having dipole-dipole forces. So what you need to remember about isomers is that they have the same chemical formula, but different sorts of arrangements, and that can make a difference in their boiling points and their intermolecular forces. Now let's talk about intermolecular forces and water solubility. So we want to think about water looking like this, where we have our partial negative oxygen, and our hydrogens here, which have positive charges. So there are 2 poles of the molecule. You want to remember that like dissolves like, and the word miscible means that it dissolves in the solvent. So they are mixable, miscible. Immiscible means that they do not mix, and that would be like oil and water. But miscible, they dissolve in one another. So polar substances will dissolve in water because of dipole-dipole interactions. The partial positive or negative of the water attracts the oppositely charged end of the other molecules, causing them to mix because of that mutual attraction. In general, solubility increases as the polarity of the solute increases. So water, this positive, partial positive, and partial negative are going to be attracted to stronger and stronger partial charges, increasing solubility because it increases the attraction. Substances that can also hydrogen bond with water are extremely soluble. Water does have hydrogen bonding, and so we've got an extremely electron deficient hydrogen here, which will be looking for unshared pairs on other oxygens or nitrogens. So if he can find something else that can polar bond, or something else that can accept polar bond or hydrogen bonds from water, then it is going to be more and more soluble, because they're going to want to mix more and more because of increased attraction. Many ionic substances will dissolve in water because of an ion dipole interaction. what happens and the reason why things dissolve. You've got like a positive sodium